Okay, so now in chapter 9, we're actually only going to do part of it. We're going to talk about how orbitals and the covalent bond fill in, and we're going to talk about something called hybrid orbitals. And then we're also going to talk about sigma and pi bonds and delocalization. So what we've done so far in the localized electron model, that is used to explain the geometry. So that's doing Lewis structures, doing the shapes. But here's the weird thing. And somebody figured this out from experiment. It's not like somebody sat down and tried to make your life difficult. They found that the bond angles, according to VSEPR and the experimental results, don't match the angles between the atomic orbitals where the electrons are. And the electrons are what create bonds. So they're a little confused, and they came up with a model to try and explain this. So in methane, we know the shape is tetrahedral. It's CH. H, H, H. Bond angle here is 109.5. They've done X-ray diffraction on it. They are 100% sure that it's 109.5. But we know that if you're dealing with carbon, which is 1s2, 2s2, 2p2, the p orbitals are on the x and y axis, which means they're at 90 degrees. And that's where the electrons live. They live in the s orbital and the p orbital. The valence electrons that form those bonds are in the s and p's, and they're at 90 degrees. And so their only explanation is that the atomic orbitals have to change when they form bonds to make a molecule. That's the explanation. And so they came up with a model called these hybrid models to account for the different angles between the orbitals, which is 90 degrees, and the electron geometry. In the case of methane, it's CH4 is 109.5. They created hybrid orbitals. So they mathematically combined the s and the p orbitals, so s p orbitals, using Schrodinger's equations, the wave functions that describe those orbitals, and they derived tetrahedral geometry at 109.5. And so what they did is took one of the s, so the 2s orbital, and the 3 of the 2p orbitals that are in carbon, and they created 4 identical sp3 hybrids. And that's where we get our tetrahedral geometry. So here's my s orbital, here's px, py, and pz. They're at 90 degrees to each other. When I combine them together mathematically, add, or whatever they did, you end up with a tetrahedron shape. And there are 4 identical orbitals. Okay. When it comes to trigonal planar geometry, they don't need all of the p orbitals to do it. They take the s orbital that they had, the carbon's 2 of the p orbitals, and they combine those, and they get sp2 hybrids. This is in something called ethene, C2H4. It has trigonal planar. The bond angles are 120 here around the carbon atoms. They need 3 equivalent orbitals at 120 degrees. And since they took the 2s orbitals, the 2p and the 2p, they took 2 of those guys plus 1s, they created sp2 hybrids. And they're identical. When you get double and triple bonds, though, because every element needs to have 8 electrons around it, there is another bond that's formed. That bond that is formed to form the extra bond doesn't come from the sp2 hybrids. It comes from someplace else. So the sp2 hybrids make what's called a single bond or a sigma bond. So right here, here's the yellow things. Those are my sp2 hybrids. They form a bond. Here's my carbon atom, and they form what's called a sigma bond. They also do it to the hydrogens out here, and the hydrogen, carbon, carbon. But what you still have is these orbitals. These are the pz, perhaps, orbitals on the carbon atoms that have an electron in them, and that's where they get what's called a pi bond. It's made out of the overlap of that extra p orbital right here. Okay, you have a sigma bond here, and a sigma bond here, and a sigma, and a sigma, and a sigma, and those are the overlap of the sp2s. Then the extra p orbitals form a pi bond. And it's perpendicular to the plane. That's why when we do geometry, it doesn't affect the geometry of the molecule because it's not part of the plane of the molecule. The plane of the molecule is right here. And that's planar because it's trigonal planar. This pi bond is above and below. So it doesn't affect the geometry at all. If you have something that's got linear electron geometry, this is acetylene or ethine as its official name. The carbon atoms take one of the s orbitals and one of the p orbitals and hybridize, and they create sp hybrids that form a single bond to the hydrogen and a single bond to the carbon and another single bond to the hydrogen. But I still have these overlap of the p orbitals, maybe px and pz or something like that, that are still left behind, and they form a pi bond, again, outside the plane of the molecule. So the remaining two p orbitals form additional two pi bonds perpendicular to the plane of the molecule. This is why when I was doing geometry, I said count double and triple bonds as one domain of electrons or electron domain because they're outside of the plane. This is linear right here. It's very obvious it's linear. Okay. So sigma bonds are created from the overlap of the hybrid orbitals and they form the electron geometry. They are a single bond between the atoms. Pi bonds are above and below the plane, and they're created from leftover p orbital electrons being shared between atoms, and that's where you get your double and triple bonds. Okay? The more bonds you have, the atoms' orbitals have to get closer together, and so the bond length shrinks. So single bond is longest, and triple bonds are shortest because they have to overlap more orbitals. Now, benzene is a little bit weird. And this is where we're going to talk about something called delocalized resonance. And it applies anytime you have something that has resonance. If you try to draw the Lewis structure of this, you have 6 times 4, you have 30 electrons to draw. If you try drawing it this way, you can't do it. You don't have enough electrons. And so they came up with this model. They were trying to figure this out. And they know that the bond lengths in between these carbons are all equal to each other. They're all the same length. But the only way they could draw the Lewis structure was to create these, they're called Kekuli structures. The bond length between the carbon atoms is shorter than a single bond, but longer than a double bond because it has this resonance. Both of these structures add up to 30 electrons. Everything has 8, and it has alternating double bonds. So they exist in resonance. So it's not like it's not a single bond, and it's not a double bond. It's somewhere in between, based on the fact that the bond lengths that they measure are all identical. And so what they said with regards to benzene and anything that has resonance, all those carbon atoms are sp2 hybridized, and the double bonds in each molecule are not trapped here. Okay, I want to contrast that with this one. That double bond is localized because it's between those two carbon atoms. These double bonds, because they exist in resonance, are delocalized, and they are perpendicular to the plane of the molecule, and they're not stuck between any two atoms. So really, a lot of times people draw benzene like this with a circle in the middle, because showing that that double bond is split out over the entire molecule, or those double bonds. So here's my sigma bond, the single bonds everywhere between carbon and hydrogen, and carbon. Those are all sigma bonds. I still have these p orbitals, and that's where it's going to form a pi bond. Right there, and right there, and right there. But they don't have to form them where I've drawn them. They could have formed them here, 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 and here. That's why they draw it this way. It's not like it's stuck in between any two atoms. It is spread out. I have 3 double bonds split among 6 atoms. So it's more like each atom has a bond and a half. So you get the sp2 hybrids. You have the leftover p orbitals right here. And that's where you form the pi bonds, but they delocalize and they spread out over the entire molecule. That's where you get resonance. And it's more like every atom in the carbon benzene structure has about a bond and a half. It's longer than a single bond, and it's shorter than a double bond. Sorry, let's put it the way. Shorter than a single bond and longer than a double bond. It's in between the two. Okay, this is a quick summary of everything. These two, I'm giving them to you, but I will not put them on the test or the quiz or anything like that. I'm just giving them to you because it just, I don't know, helps explain it. All right, so identifying the hybridization of each atom. So this is a big Lewis structure. It's methyl salicylate. It's wintergreen. And we want to identify the hybridization of any atom other than hydrogen. So we don't look at hydrogen ever when it comes to hybrids. You're only looking at carbon and oxygen. And what you do to figure this out is you count the number of things the atom is attached to. So a lone pair counts or an atom counts. A double bond is one electron region, so you don't count it. So if I'm looking at this carbon atom right here, I see it's attached to 1, 2, 3 things. So that carbon atom right there in the center is sp2. This one is attached to 1, 2, 3, sp2. 1, 2, 3, sp2. 1, 2, 3, sp2. 1, 2, 3, sp2. And sp2. This carbon is attached to 1, 2, 3, also sp2. This oxygen on the end, we're going to figure out its hybridization. 1, 2, 3, also sp2. This oxygen in the middle, we're going to figure out its hybridization. 1, 2, 3, 4, that's sp3. And the carbon on the tail end, 1, 2, 3, 4, sp3. This oxygen, 1, 2, 3, 4, sp3. Okay, notice I didn't do anything with the hydrogens with that. All right, let me erase all the ink. How many sigma bonds and how many pi bonds? Easiest way to do that is find the total. So I'm just going to go through and count every line. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So I counted every line. Total number of bonds is 23. Now the easiest way to figure out which ones are sigma is actually to go through and figure out which ones are pi. Because the total number of lines has to add up to 23. Inside here, one of those double bonds is a pi, one of those double bonds is a pi, one of those, and one of those. So I see 4 pi bonds. That means I have to have 19 sigma bonds because they have to add up to 23. Okay? What are the approximate bond angles? I'm going to erase the ink again. A through E, I didn't write that in here. This is A, B, C, D, E. It doesn't really matter as long as you kind of pay attention to it. So A, B, C, D, and E. A is sp2 hybrid on that carbon atom. So the carbon-carbon hydrogen bond right there, bond angle, is 120. If I look at B, this oxygen atom is sp3 hybridized. So the COH bond that's represented by the B is 109.5. You don't do bonds with lone pairs because you don't quite know where they are. Okay? Over here, this carbon in the center is sp2 hybridized. So we're looking at the carbon-carbon-carbon bond. It's 120. This bond right here is centered around the oxygen, which is sp3. So carbon, oxygen, carbon is 109.5. And this carbon over here, same thing. It's a sp3 hybridized, 109.5. Very weird stuff, not super hard.